Hello, welcome. This is Logan Van Gheem. Here is my physics video walkthrough. I essentially asked ChatGPT to generate a problem that would be able to incorporate all the main forces seen within circular motion. So the following goes: a small 1.2 kilogram model airplane is attached by a string to a pivot above the center of a circular track. Radius r equals 2.5 meters. The airplane flies at a constant speed, v equals 8 meters per second, while climbing from a horizontal flight into a vertical loop that sits above a frictionless banked turn angled at theta equals 18 degrees. And we're going to assume that gravity equals 9.8. So for part A, we're going to find the tension while flying horizontally. For part B, we're going to be finding the tension at the bottom of the vertical loop. For part C, we're going to find the minimum speed needed at the top of the loop to keep the string tight. And then for D, we're going to find the ideal speed for the banked curve, which, as I noted right here, we do not need friction. So even if this was not frictionless, it wouldn't theoretically matter, at least for our purposes. So for part A, we're going to be using the following tension equation, which is mass times the velocity, which is going to be squared, that times the radius. I'm going to square the velocity outside the equation for right now. You can just do it. You can just write the 1.2 kilograms, 8 squared over 2.5. 8 squared, that's up to 64. So 1.2 times 64. Also that divided by 2.5 gives us a value of 30.72 newtons, which would be the tension while flying horizontally. For section B, a section is going to look really similar to this. We're going to take a section from the part A to be using here. So this equation right here looks probably awfully familiar, and it should look awfully familiar since it's that right there. But we also do have to add a final part to it, which is the normal force, which is mass times gravity. So plugging into the values, we're just going to plug this value in for that equation right there. So 30.72 newtons. It's going to be added to, we know the mass already be 1.2 kilograms, and because it's in kilograms, we don't have to change anything of that. And then 9.81 meters per second squared for the gravity, which was established up here. So adding these values up, we're going to get 30.72 newtons plus 11.772 newtons, which obviously those added together will get a final value of 42.492 newtons, which will be the tension on the string at the bottom of the loop. All right, for part C, we're going to find the minimum speed needed at the top of the loop to keep the string tight. So we're essentially going to take the following function, which is mass times gravity, mass times the velocity squared minimum, times the radius. We want the velocity. That's what we want. So we're going to multiply the radius to both sides. So mass times gravity times r, which equals mass times velocity squared min. Now, one thing you might notice immediately, and you can do this right away, I didn't, is mass is on both sides, which means we can do this. And mass will cancel. So these values go bye-bye. So then we just get gravity times the radius, which equals the velocity squared minimum, which we do want just velocity. We do not want that value squared, so take the square root of both sides. So the square root of gravity times radius, or times the radius, equals the velocity minimum, or the minimum velocity. Plugging in the values, we get 9.81 times 2.5. Once again, these are in meters. This is in meters per second squared. All of these square rooted, which gets us the final minimum speed value in order to keep the string tight, keep the string in a nice tight state. So 4.95 meters per second. All right, then. So then for part D, we're going to be finding the ideal speed on the banked curve. So we're going to take the following function, which is the tangent of theta. It has a really bad theta. Equals velocity squared times the radius, or divided by the radius, which is times gravity. But what we want is the velocity. Once again, we want this value. So to make the equation pretty much function very similar to this guy up here, we're going to multiply the whole equation. We're going to multiply both sides by the radius. So it's our radius times tangent theta, which equals the velocity squared over gravity. Then same process, multiply by gravity on both sides. So it'll be the radius times gravity times the tangent of theta, which equals the velocity squared. And similarly up here, we are going to be taking the square root of both sides. So it'll be the square root of r times gravity which equals the velocity. Solving for that, we'll end up getting the final value of 2.82 meters per second. Not that too close. Which is going to be the ideal banked speed. So pretty much this covers just about all the topics that are relevant to, or not all the topics, but the main core topics involved with circular motion. So hopefully this helps. But of course, for sanity's sake, and I do recommend doing this if you have time on an exam or test, is to essentially do, I like to refer to it as a sanity check. So we found for section C that the speed is 4.95 in order to, the minimum velocity, needed to keep the string tight is 4.95 meters per second. But we want to make sure that is the correct value. We can simply just plug the value into the function. Try a C check. So plug it into values. We know it's a 1.2 kilogram auto airplane. We found the speed to be 4.95 squared, which we're going to square that as per the original function, divided by 2.5 equals 1.2 kilograms, 24.5 for the speed or the velocity, and then of course the radius is still 2.5 meters. Continuing on, the numerator we'll get 29.4, and on the denominator we'll get 2.5, which gives us a value of 11.76 newtons. So that's on the left side of the function. Obviously there is the right side of the function still, which is mass times gravity. So 1.2 multiplied by 9.81 as established before, which gives us 11.77 newtons, which these are within, I guess, spec, if you want to call it that. So yes, it is confirmed that that is the correct minimum speed needed to keep the string taut. All right, so that was just for part C. All we do is check part C, but we still need to check part A, B, and D. So for the A check, I also do want to mention you don't have to write this out like A check. Obviously, this is how I'm organizing it. Do whatever you want, pretty much, just as long as you can understand it. So obviously, I should have mentioned this before, units. So obviously we had a mass, so the mass of the model aircraft, or model plane, was 1.2 kilograms. We know theta equals 18 degrees. We know the velocity that the airplane was traveling at was 8 meters per second. We obviously know gravity was established to be 9.81 meters per second squared, which could also be written as meters divided by seconds. Whatever is easier for you to understand. The radius which the plane is traveling in is 2.5 meters. For part A, we had to use the tension equation, which was the mass times the velocity, which is squared, divided by the radius. We just want to verify that, probably the quickest way to verify if this is correct, essentially. It's honestly just checking, like, do the units properly correlate with newtons, which is the target. If we just plug the units in, our units are kilograms, meters per second for the velocity, that is squared, divided by meters, which that would equal just kilograms multiplied by meters over seconds squared, which that obviously comes out, which this right here is what's underneath the umbrella, if you want to call it that, represents newtons, which is the goal. So another thing you always could check, and this goes for any physics problem, is kind of just thinking about it from a realistic standpoint. Like, is it possible for the tension on the string of the plane to be some exuberant number? Like, it's not going to be 100 and some thousand newtons. Or you almost could tell just by reading the problem if it's going to be a very outlandish answer. So obviously just thinking about it from a very common sense standpoint of just, is this right or is this wrong? All right, so the second way of testing for part A, because this just tested the equation. This did not test if our answer was actually correct. Like if you accidentally typed one of the numbers wrong into your calculator or what have you. So pretty much the best way to see that is plug it back in. So real quick, we're going to do a plug check. From here, calculate the centripetal acceleration. So that is simply the velocity squared divided by the radius. So we know that 8 was the velocity, that square is 64, divided by the radius, which we know to be 2.5, which comes out to a value of 25.6 meters per second squared. From here, just plug and chug. So the values we'll be plugging in is simply the mass, which we know to be 1.2 kilograms, multiplied by the number we found up here, which is the centripetal acceleration. So it would be 1.2 which comes out to a value of 30.72 newtons. This uses a slightly different method of solving, but it's honestly pretty much the exact same thing. But this is another good way of confirming your result, is by using another function to see if you get the same value back. For part B, so pretty much you could do the same thing, verifying that all the units cancel out properly and essentially just double checking the equation to make sure the equation is in tip-top shape. You don't have to do that necessarily, but if you just want to find if your value is actually correct, probably the quickest way of finding that out is just, once again, kind of plug in a chug. So we have our tension at the bottom of the circle subtracted by mass times gravity, which are both in newtons. So 42 point, which we found for the tension at the bottom to be 42.492 minus 11.772, which comes out to 30.72, which is equal to the mass times velocity squared over radius. So that's a really simple just check. All right, so for the part D check, I have something to solve right now here. First, we're going to solve for the tangent of 18 degrees, which we know to be roughly 0.3249. There are more digits after that, and I do recommend carrying it down if you're using a calculator. But for simplicity's sake, we're going to leave it at this. From here, you plug it into pretty much the exact same equation we used back in part D. So that'll be the radius times gravity times the tangent, tangent of theta, and that is equal to the velocity squared. So plugging in the values, we know our radius was 2.5, we know the gravity was 9.1, and of course we found the tangent value over here. And that is of course equal to the velocity, which is what we're trying to find. So plug in the numbers. On this side, you should end up getting 9.67, which obviously we can't leave the square root on top here. We need to get rid of that. So taking the square root of both sides, we'll end up with a velocity of 2.822 meters per second. So taking this value, so obviously this is one route you definitely could take for checking. Just redoing it again, but of course that's not always the best case. So pretty much just plugging the values back in. Or from here, pretty much we just do everything in reverse. So we take the value, square it, we'll end up getting 7.967, which should be the same value you found over here. From there, just simply take this number divided by the radius times gravity, which should roughly give you the value of tangent, which was tangent of 18 degrees. So solving this out, we'll end up getting pretty much within the ballpark of, we'll end up getting pretty much the exact value, or we'll be getting the exact value. Pretty much we'll be getting a very similar value to what was found in tangent. And depending on rounding, that value could change a little bit. But like I said, if you're using a calculator, I recommend carrying that down. The final main that you could use to check is honestly kind of looking at it from a common sense standpoint. Like if the numbers are very small, unless you're going from meters down to essentially going from kilometers down to millimeters, the value really should not change that extreme. And even then, the answer you get should be within a reasonable expectation. So you're not going to get, for the velocity here, you're not going to end up getting 600 or something. Obviously incorrect. So that's probably the best way, that's probably another good way to check if it's yay or nay. So pretty much that is the full walkthrough of my following problem, which I did generate from ChatGPT. And we did end up finding all of these values. Wish you luck. Thanks for watching, and I hope that this gave an appropriate explanation.